All right, let's talk about Newton's second law of motion. The sum of the forces equals ma. We got a car right here. There's a forward force in the car of 1,000 newtons, and there's a force of air resistance of 400 newtons. So you can see that there's a net force to the right. So that means that car is going to accelerate to the right. So acceleration always occurs in the direction of the net force. So we go ahead and draw a force diagram. We can go ahead and show a force 1,000 newtons to the right and a force of 400 newtons to the left. This is 1,000. And this right here is 400. So this is a force diagram. There's a net force to the right. Some of the forces in the x direction equals ma. 1,000 newtons minus 400 newtons equals the mass of the car. The mass of the car, I didn't tell you, is 1,000. Oh boy. 1,000 kilograms times A. If we go ahead and solve that right there, we have 600 newtons on the left-hand side. We have 1,000 kilograms on the right-hand side. Times A. And if we solve for A comes out to be 0.6. 0.6 newtons per kilogram, which is equivalent to 0.6 meters per second squared. And that car right there will accelerate at a rate of 0.6 meters per second, positive 0.6 meters per second every second. It's going to increase in velocity to the right. So this always works. It will draw the force diagram and apply this law. Let's look at skydiving. We got an airplane here. There's the airplane right there. Like that. And person jumps out of the airplane. Like that. Their mass is 80 kilograms. So when they first start falling, they don't have a lot of motion downward yet. So the air resistance is very small. So we go ahead and draw a force diagram for this person when they first jump out of the airplane. We can show a force diagram like this. This downward force is equal to 80 times 10, which is 800 newtons. As a matter of fact, I'm going to take that back. I'm just going to say the force of gravity is their mass times acceleration of gravity. So there's our force diagram right there. And if we go ahead and apply Newton's second law of motion, F equals ma, the net force, and this is going to be in the y direction, up and down. So this law only applies to one direction at a time. Over here, we did the x direction. Now we're going to do the y direction. The force, overall force, is minus mg equals ma. You can see the masses cancel out, and the acceleration is negative g. So that proves right there that when things fall, that they fall with acceleration of negative g or negative 10 meters per second squared. So everything, regardless of their mass, in the absence of air resistance, will fall downward with an acceleration of 10 meters per second squared. That's kind of cool. Mass doesn't matter. Now, so this acceleration is going to cause the skydiver to start to increase in velocity downward. Increase it with a rate of 10 meters per second every second. As this person increases in velocity, the air resistance will actually increase. So let me go ahead and show that downward force. Now a downward force of 80 times 10, which is 800 newtons. And there's an air resistance here. Let's say we figure out the air resistance, and the air resistance is a little more complicated to figure out. But let's say the air resistance is 300 newtons. You can see this problem is almost identical to this problem over here. This is a different direction. So we approach it the same way. Sum of the forces in the y direction equals ma. So we got 300 newtons up minus 800 newtons down equals a mass of 80 kilograms times A. So we solve this right here. We got negative 500 newtons divided by 80 kilograms. That gives us the acceleration. Acceleration, 50 divided by 8 should be 6.25, so about 6.3. 6.3 meters per second squared, and there was a negative there. So we can see this person is still accelerating downward. We know they're accelerating downward because the force down is bigger than the force up. Therefore, this person is going to accelerate in the negative direction. This will cause the person to continue to increase in velocity. This person is going to increase the velocity of negative 6.3 meters per second every second. So this person is still getting faster, just not getting as fast, if that makes sense. So because you're moving faster, the air resistance increases. Eventually what happens is the air resistance will eventually reach the same size as the person's weight. So this person has a weight of 800 newtons. 800 newtons. And when they move it fast enough, what happens here is this person's air resistance will actually match their weight. So this air resistance eventually becomes 800. And you can see now that this force diagram no longer shows a net force. This shows an equilibrium here. The force up is equal to the force down. And we've learned that that means either it's at rest or it's moving at constant velocity. Since this person's already moving, we can go ahead and say this person's moving at a constant velocity. F equals ma. This is going to be in the y direction. We have 800 newtons going up. We have 800 newtons going down. Is equal to the mass of 80 kilograms times A. And you can see right here that A is going to equal 0. This person moves at a constant velocity. And this is called terminal velocity. Terminal velocity for when people jump out of an airplane, they just free fall. They'll eventually get to about 140, 150 miles an hour, depends on their surface area. But they'll reach terminal velocity, and that's the point where they will no longer increase in velocity. All right, so a few examples of F equals ma. The steps are: draw a force diagram, a good force diagram, write the law down, and go ahead and plug the numbers in and solve. You'll do that every time. You should have success with these problems. All right, let's talk about elevators now. I'm sure you've all ridden in an elevator before. So here's a person inside the elevator, and they stand on a scale. This person has a mass of 80 kilograms. 80 kilograms. And let's say this elevator accelerates upward. Go ahead and give it an acceleration upward of like, let's say 3. So the acceleration is 3 meters per second squared. And you've all felt that before. When you get inside an elevator, you first take off, you first accelerate. You can kind of feel that. In fact, for me, it feels like I'm heavier. And if I stand on a scale, if I feel like I'm heavier, I wonder if I really am heavier or not. Let's look at this with the force diagram. Let's draw a force diagram of the actual person. There's a person right there that represents a person. And the person has a force of gravity of 800 newtons. And this person is going to accelerate upward at 3, which tells us that the force up has got to be bigger than the force down. I didn't leave myself much room on this problem. But the force up, which we call the normal force, has got to be bigger than the 800 down. Let me redo that normal force there. Let's see if I can write again. That looks a little better. So the force up is bigger than the force down. And you know what? These force diagrams are important. So I'm going to go ahead and I'm going to get rid of this guy right there. And I'm going to draw it so that it's definitely shows the smaller force. So that looks better. Okay, so I've got this person on the elevator. The normal force will actually read what the scale says is actually the normal force, which shows your apparent weights. So you can see that the scale, according to this force diagram, will actually read more than 800 newtons. Then we look at the Newton's second law of motion. Some of the forces in the y direction equals ma. We can see normal force minus 8,000 newtons is equal to the person's mass, which is 80 kilograms, times acceleration, which is positive 3. And so normal force, in this case, is to be 800 plus 240, 1,040 newtons. This person normally weighs, if they just stand there on a scale, They normally weigh 800 newtons, but because the elevator is accelerating upward, they actually weigh more. And you can see that if this acceleration were to get even bigger, the normal force would get bigger as well. We can also look at a person in an elevator that's accelerating downward. And I'm sure you felt that before as well. You know, you're in the elevator, and then as you get close to the top, near the top, you feel kind of weird. You feel a little like little like you weigh a little bit less. Your stomach kind of does some weird things. At least mine does. And let's say in this case, as you start to slow down, as you go up, you're going to have a negative acceleration. Let's say your acceleration is acceleration. Let's call it -2. Acceleration is -2. And so again, we can go ahead and draw the force diagram. And normal force, since this elevator accelerates downward, we know that the force up is going to be smaller than the force down. So we got normal force right there. If we go ahead and look at it, F, some of the forces in the y direction equals ma. We have normal force going up minus 800 newtons going down is equal to the mass of 80 kilograms times the acceleration of -2. Like that. And if we solve that, we get normal force 800 minus 160. That's going to be 640 newtons. So you can see this person is going to weigh less because of that negative acceleration. Negative acceleration causes you to weigh less. And if I were to ask you, you know, if you were to look at the situation at elevator, and you were in the elevator, and let's say your acceleration is 0 in this case, which means constant velocity. You can see in that case, we have a force of gravity of 300 still, and we have a normal force. If it's at constant velocity, these have to be the same. So 800 newtons going down, you got normal force going up. And you can see if you're moving at constant velocity, that this is a situation with equilibrium, which means normal force is going to equal the 800. So it's just like saying on a scale in a room. So constant velocity doesn't cause a change in your weights. So 3 more examples of Newton's second law of motion. I'm going to show you one more today. I want to talk about this right here. Talk about inclined planes. We've done some work with these before. And let's say that we have a car that's going to roll down this inclined plane. Yeah. And we'll go ahead and call this angle, we'll call it 30 degrees. The mass of the car, I'm just gonna call it, let me call it M. We don't know the mass. So we're gonna go ahead and look at this and apply Newton's second law of motion to figure out this car's acceleration as it rolls down the inclined plane. We're assuming no friction. We're assuming the wheels are not that big. So we're assuming ideal circumstances here. So let's look at this car. First of all, we have the inclined plane. Inclined plane, same angle as the inclined plane. Here is a car, and we have force of gravity going down like that. We're going to call that force of gravity M and G. And we also have a normal force. A normal force is going to be perpendicular to the surface, about like that. We'll go ahead and call that normal force. Like that. This angle right here, this is the y-axis. This angle right here is 30 degrees. And that should be everything. That's all the forces. This is a force of gravity, which always acts straight down. Normal force acts perpendicular to the surface. We said there's no friction. So this is everything. So we'll go ahead and do what we've done before and find the x and y components. We see that this force of gravity acts in the x direction, like that. And it also acts in the y direction, like that. If the car is not moving up or down, these two should be the same size. So I'm going to do it again. I'm going to redraw this and make sure those two are the same size. So here's the inclined plane. Here's the car. And we have a x component like this. And we have a normal force and a it's a pain. We have the y component of the force of gravity. Let me come back over here and finish this. I didn't do a very good job finishing this. This is the force of gravity mg. This is a force that's in the x direction. So we're going to go ahead and say mg times the sine of 30. And this right here is going to be mg times the cosine of 30 degrees. So let's go ahead and this is normal force. This right here is going to be mg times the sine of 30 degrees. That corresponds to this right here. This is the component that is parallel to the plane, which is right there. And this over here is going to be mg times the cosine of 30 degrees. We can see that this is going to equal the normal force. But these two will be the same magnitude. So there's no acceleration in the y direction because those have the same magnitude in the opposite direction. But this right here has a net force. There's a force down the plane. And when there's a net force, there's an acceleration. So we're going to say some of the forces in the x direction equals ma. I'm going to go ahead and call this direction right here. I'm gonna call that positive. So if I did that, what I would have is I would have m g sine of 30 is equal to m a. Look at that. The masses cancel out again. Masses cancel out. And we get acceleration right there of g sine of 30. So 10 sine 30 is 0.5. So 10 times 0.5 is going to be 5. So 5 meters per second squared. It's how that car accelerates. How that car accelerates. You can see that the mass cancel out, so it doesn't matter. The mass of the car does not make a difference. It always accelerates at 5 meters per second squared if the angle is 30 degrees. All right, so let's go ahead and let's do one more problem. I want to give you a chance to try one on your own. Probably the best way to learn this is actually try it out. So this time, I'm going to mix it up. I'm going to go in the opposite direction, like this. And let's see if my car looks any better this time or not. Probably not. Let's see. It's not really that much better. Go ahead and make this a 60-degree angle. Like that. And we'll just say the mass of the car is mass M. So if you want to learn this stuff, then go ahead and press pause and try to find the acceleration of this car on your own. All right, so press pause. All right, welcome back. Now let's go ahead and give this problem a try. Let's try the acceleration of this car right here. So what we talked about doing is, first of all, drawing a force diagram. So here's a car, and we know that it's going to accelerate in that direction. So this inclined plane right here, this is our x direction. We'll call that positive right there. And we have a force of gravity that is straight down. We'll call this mg. And we have a normal force, which is perpendicular to the plane. So that's normal force right there. And let's see here. This is that's a y-axis. This angle is going to be 60 degrees. You ask why? Well, we look at this problem. That's our weight vector right there. And so that weight vector makes a right angle with this with the horizon there. And so this is 90, that's 60, this is going to be 30. So it adds up to 180. And then we look at this part right here. This is y-axis. This is perpendicular to the plane. And so since that's a right angle, 30 plus 60 has got to equal 90. That's why we have 60 right there. Let's go and break this up into the x and y components. So we got that. And we got that right there. So we got mg times the sine of 60. This is going to be mg times the cosine of 60. So if we go ahead and got the Oh, inclined plane. Yeah, y-axis right there. If I go ahead and redraw this right here, then there's my x components. And got my y component. I got my normal force right there. This is my normal force. This is going to be mg sine of 60. This right here is going to be mg cosine of 60. Normal force and mg cosine 60 will basically that force is equal to 0, so there's no acceleration in that direction. But in the x direction, you can see that we have a net force in the x direction, so it's going to accelerate down. Sum of the forces in the x direction equals ma. So we got mg sine of 60 is equal to ma. Masses again cancel out. And if you solve for a, mg times the sine of 60. Sine of 60 is radical 3 over 2, about 0.87 times 10 would be 8.7 meters per second squared. So there's your acceleration right there for a 60-degree angle. All right, so hopefully that helps. These acceleration problems. Draw for a really good force diagram. And write down F equals ma. Some of the force equals ma. Make sure you just use one axis only. And then plug and chug. All right. Have fun. Physics.